let's discuss this problem, right? So now air enters a window air conditioner at 1 atm, 30 degrees Celsius, and at 80% relative humidity at a rate of 10 meter cube per minute, right? While it leaves as saturated air at 14 degrees Celsius from the outlet, okay? And the next part of the moisture in the air that condenses during the process is also removed at 14 degrees Celsius, right? Now they're asking two things, right? Calculate the rate of heat removal from air and calculate the rate of moisture removal from air, right? And in order to perform this calculation, right, we need to know saturated liquid enthalpy of water, right? This actually you cannot find from the psychometric chart, right? Okay, what is this? Saturated liquid enthalpy of water, 58.8 kilojoules per kilogram at 14 degree Celsius, right? So now this question is based upon the concept of cooling and dehumidification, right? So now under this problem, right, air is cooled, right, and dehumidified, right, by considering the entire process as a steady flow process, right? And before solving this type of problem, right, there are certain things that you should know, right? So without knowing that fundamental path, right, it will be really difficult for you to solve this problem, right? So here you can see, right, now if you are going to consider this window air conditioner, right, there are certain directions, right? See, this is the input direction, right, and this is the output direction, but this is not the only output direction, right? Because the reason why here we have condensate removal at 14 degrees Celsius, right? Again, read the problem, right? So don't just memorize the problem, right? Or don't just memorize an already solved problem, right? Just understand the concept and especially the directions, right? So now here there is a very special point that you must know, right? So now as this is a steady flow process, right, the mass flow rate of dry air, right, will remain the same, right? That is a very important point that you must know. Actually, when solving this problem, right, the kinetic and potential energy changes are considered as negligible, okay? When solving this problem, right, the number one thing is that you have to find the thermodynamic properties or the parameters for the input side, right? So now what are the initial information, right, that are given to us, right? So they have given us the temperature and the relative humidity, right? Temperature, they have mentioned it as the dry bulb temperature, that is 30 degrees Celsius, and the relative humidity as 80%, right? Because okay, first of all, let's write the let's include the values, right, that we have to obtain from the charts, right? So we are going to use the psychometric chart, right, at sea level, because now in this problem it is very clearly mentioned that because like even in the introduction video, right, I have told you that when using psychometric chart, it must be specified that what is the particular pressure where the chart is made, right? So it is at the barometric pressure, right? Okay, so now what is the input side, right? Now this is the input side, right? So let's put it a label, right? So the label 1, right? So label 1 is the input side, right? And this is the output side, right? And this is not the only output, right? But in between the process, right? Because no, this is the like extreme outlet, right? This is where we have air in, right? And this is air out, right? But in between that, I have previously told you, right, we have that condensate removal process that is in between, right? Anyhow, this is also a kind of an outlet, right? Because like whatever the energy that whatever the energy, right, that is provided to the system over here, right, and it outputs that energy at two different places, right. So one is at here, the other one is at here. Okay, but okay, let's consider for input side, right, it is given that dBT, dry bulb temperature, as what, 30 degrees Celsius, and relative humidity as 80%, right. So now you know how to use the psychometric chart, right, the boot shape, right. So then, right, now when considering the input side, right, we need to find certain parameters, right. So those are actually H1, which is the specific enthalpy, and then omega 1, which is the humidity ratio at the input side, right, and specific volume, right, V1, right. Okay, specific volume, right. Okay, so then how to find the specific enthalpy, right. So you know that in order to refer the psychometric chart, right, basically we must know two parameters, right. If you know two parameters, then you can find the rest, right. So relative humidity is given, right. So I have previously taught you that it is something like, like a sari, right. Okay, some curve like that. See, relative humidity, something like this. Okay, so let's call this is 80%, right. Now at the moment when I'm teaching, right, so you better refer this chart, right, 80%, right. And what is this 30 degrees Celsius? That is the dry bulb temperature, right. So this horizontal scale is the dry bulb temperature scale, right. And locate where you have 30 degrees Celsius. So let's say 30 degrees Celsius dry bulb temperature is over here, right. And I have taught you that dry bulb temperature lines, right, go vertically, right. So select the correct dry bulb temperature line that indicates 30 degrees Celsius, right, then go like a straight line. Okay, and at here you will find that intersection, right, intersection of the 30 degrees Celsius dry bulb temperature line with the 80% relative humidity curve, right. So this curve is the relative humidity, right. Now from this point, right, from this point of intersection, right, you project a line horizontally, right, until it intersects with this vertical scale, right, and there you can find the humidity ratio, right. That means a kilogram of moisture per 1 kilogram of dry air. So that will give you the value for omega 1, right. So if you carefully find that from the specified psychometric chart, right, you should obtain omega 1 as, I already have the answers. Let's see, omega 1 should be 0.0216 kilograms of moisture per kilogram of dry air, right. So omega 1 is okay, right. And next thing is the specific volume, right. There you have to be very careful, right. So now I have taught you, right, that specific volume lines are the lines, right. It's a line like this, right, that so specific volume lines, right. So if you're going to consider one specific volume line, right, approximately, right, it makes an inclination, right, with the left horizontal, right, at an angle about 60 to 70 degrees Celsius, right, somewhere like this, right. Okay, so definitely when solving a real problem, right, so you will never ever get a line, right, that exactly passes through that point of intersection, right? So you have to be very careful. So that is why every time it is strictly advised, right, to use the ruler, right? Because like now how the pattern of lines, right? The pattern is that these lines go in kind of an inclination, right, with the left horizontal, right? So you have to use your ruler and you have to consider parallel lines, right? Because definitely there will be no an exact line that passes through the point of intersection, but one line, just consider one particular line, right? Then project it parallelly, because the lines are going like this, right? So then use the ruler and just uh, consider a same line, right, that is parallel to one of the specified lines that actually passes through this point of intersection. You got it, right? So then you can determine what is the specific volume, right? So if you carefully obtain that, the specific volume must be 0.889. It is 0.889, right, meter cube per kilogram, right? Then enthalpy, that for specific enthalpy also there's a different scale, right? Specific enthalpy somewhere here, right? This line indicates what? Specific enthalpy, right? So now there also you have to consider the same concept, right? Because we know that the same line, right? The same line that indicates the wet bulb temperature, right? So that same line is extended to a different scale that shows the specific enthalpy, right? So they also definitely will not find a line that exactly passes through the point of intersection, but the pattern of lines, right? So that if you're going to consider wet bulb temperature line, right? If you're going to consider one line that represents the wet bulb temperature, right? It makes an inclination roughly like 25 to 30 degrees with the left horizontal, right? So there also, if there is no a specified line that exactly passes through the point of intersection, then you have to follow the pattern, right? Shall I draw it here again? Now let's consider that this is our point of intersection, right? This is 80% relative humidity and this is 30 degrees Celsius dry bulb temperature, right? So now we know the pattern, right? What is the pattern? Now this is the pattern, wet bulb temperature, right? Now let's say we don't have, now as an example, let's say that we don't have a specified line, that is we don't have an exact line that actually passes through the point of intersection. So then we can actually imagine such type of a line, right? That is why you need the, actually here in this case you need actually two rulers, right? So one rule is there that you can place on one line, right, that is very much closer to the point of intersection, right? So now if there is no exact line that passes through the point of intersection, then you have to imagine such type of a line, right? So for that you need to keep your ruler at one known line that is very much closer to the point of intersection. Then right, in order to lock that position, right, in order to project, right, parallelly, you need another ruler. Now let's consider this is the other ruler, right? So then now you can project. You got it, you get my point. Now you can project, right? Then use the pencil, right? Now you know that, okay, right? So now project this line from here to here, right, to the scale that gives the specific enthalpy, right? So then specific enthalpy is also known. I hope you know that, right? And okay, and the other thing, right? So now all the input parameters are known for the input side, right, over here, okay. And then if you're going to consider this condensate removal scenario, right, in this question, right, so they have actually provided us what is the enthalpy of saturated liquid water, right? So now enthalpy of saturated liquid water that you cannot find from this chart, right? So that is what is given, right? So for this side you need to know what is the enthalpy of saturated liquid water, right? That is actually given, right? So that is 58.8. That is 58.8 kilojoules per kilogram, right? So without that you cannot proceed, right? And then we'll consider about the other side. What is the other side? Now again read the problem very carefully, right? Now in this problem it is clearly mentioned that it leaves as saturated air at 14 degrees Celsius, right? Again be very careful, right? So it says that if I'm going to consider the extreme outlet, right, position number 2, right, leaves as saturated air at 14 degrees Celsius, right? So now then if you want to find the thermodynamic properties according to that scenario, right, so this is the concept, right? So okay, I will again sketch another boot here, right? So now it leaves as, be very careful, saturated air at 14 degrees Celsius, right? So now you know this is the curve of saturation, right? Where the relative humidity is 100%, right? So this is the 100% relative humidity line, right? So now select what is 14 degrees Celsius dry bulb temperature. Now let's okay, so 14 degrees Celsius dry bulb temperature line is here, 14 degrees Celsius, right? So now from this 14 degrees Celsius point, right, sketch this vertical line, right? This 14 degrees Celsius dry bulb temperature line, right, will get intersected with the 100% relative humidity curve. Here we have the 14 degrees Celsius dry bulb temperature line, right, that goes vertically, right? And you know this curve, right? So this is the curve of saturation, right, where the relative humidity is 100%, right? So now here you need to find what is the point of intersection with this 14 degrees Celsius dry bulb temperature line and this 100% relative humidity curve. Project this point of intersection horizontally until it again intersects with the humidity ratio scale, right, that is at the right hand side, right? Because you know this scale, right, represents the humidity ratio, right? So that will give you what is omega 2, right? So if you carefully focus the values, right, if you carefully find that point, right, so omega 2 will be 0.01. If you carefully focus, omega 2 will be, to output side, right, omega 2 will be 0.01 kilogram of moisture per kilogram of dry air, right? So it is done. And how about the specific enthalpy, right? Again this point of intersection, right, as I have taught you for the previous scenario for the input side, right, you know the procedure, right? So now you can find the specific enthalpy H2, right? Find that particular line that represents the specific enthalpy of a line that is actually closer to this point of intersection, right? So then after using that, after using two rulers, right, then project it, right? So then you will find what is the specific enthalpy, right? So if you carefully find, it must be 39.3, right? 39.3 H2, right? 39.3 kilojoules per kilogram, right? Now be very careful, please check the values, right, because you should know that method, right? Now we have obtained all the necessary thermodynamic properties, right, the values, right? So now just focus that this problem is based on cooling and dehumidification, right? So now actually what happens under dehumidification, right? So under that, if you are going to consider the humidity ratio, right, at the stage 1 is omega 1, right? As this problem is based upon dehumidification, cooling and dehumidification, right, then what will happen now? If I am going to say omega 2 is the humidity ratio at stage 2, right, which is the ultimate outlet, then definitely omega 2 will be lesser than omega 1, right? That means definitely omega 1 is higher. Got it? Right. Now, now we need to obtain some balancing equations, right? What? Balancing equations, right? Right. Basically, we need two types of balancing equations, right? Number one, balancing dry air mass, right? Right. And the second one, right? Balancing, right, water mass, right? Okay, because we know that air contains some vapor, right? And now the next most important thing is that I have previously taught you that when solving this type of a problem, right, it is very much important to know about the circuit, right, to know about the path, right? So now what is the path? This is the input and this is the output, right? But in between that we have a process that is called condensate removal, right? So now first of all we will consider balancing dry air mass. Okay, first of all we will consider that. Later we will come to the balancing of water mass, right? Okay, so now air enters from this position, right? That means air enters from this stage, right? And then air exits, or in other words the outlet, right? Then air exits from here, exit, right? So let's say the dry air mass flow rate, right? The flow rate of dry air mass, right, that enters, right, is ma1 dot, right? And dry air mass, right, that exits at the outlet is, let's call it ma2 dot, right? So now what can you say about that, right? If you're going to consider the entrance and outlet, definitely you can very clearly say that ma1 dot mass flow rate equals ma2 dot, right? This dot stands for flow rate, right? So as both of these are equal, right, as ma1 dot equals ma2 dot, right, we can simplify it, right? Because you know that this type of simplification techniques are very much important, right? Because if you are taking too much of terms and components into the problem, it will be very difficult to solve. ma1 dot equals ma2 dot equals, let's call it ma dot, right? Okay, so now you know what is ma1. What is ma1 dot? Dry air mass flow rate from the entrance, right? So what is ma2 dot? That is the dry air mass flow rate at the outlet, right? The next thing, right? So now let's focus balancing of water mass, right? So now you know we have something called humidity ratio, right? HR, humidity ratio, HR, right? That is the amount of water vapor, right? That is there in 1 kilogram of dry air, right? Humidity ratio, right? Like if you're going to consider humidity ratio, right, there's a special symbol called omega, right? Okay, so that means we can say that omega equals, right, amount of water vapor that is there, V divided by MA, right? Right. So now when considering the mass flow rate of water vapor, right? So now there we have to consider uh, several paths, right? So what is the path number one? That is the input, right? Because we get air from the entrance, right? So there we have to consider what is the mass flow rate of water vapor, right? That enters to the system from the entrance side, right? So let's call it mv1 dot, right? And the mass flow rate of water vapor at the outlet, right? So let's call it mv2 dot, right? Now you know that under this problem, right, this question is based upon dehumidification, right? So then definitely omega 2 will be lesser than omega 1. Got it, right? And also we know that there is a formula for omega, which is the humidity ratio, right? That is what we call as mass of water vapor divided by mass of dry air, right? And if you are going to consider it as a unit, it is the amount of moisture that presents as measured in kilograms divided by 1 kilogram of dry air, right? That means if you are going to consider 1 kilogram of dry air, right, what is the amount of water vapor that presents in kilograms? Very important, right? Be very careful about the units, right? So now for that we can actually write a very clear equation, right, when considering the balancing of water mass, right? I will write it again. So now we know that omega equals what? mv divided by ma. Got it, right? So then we can say, when considering the entrance scenario, we can say that you know that at the entrance the humidity ratio is omega 1, right? Okay, at the entrance the humidity ratio is omega 1, right? So omega 1 equals mv1 divided by ma1. But be very careful here, actually we are going to consider the flow rate, right? Because in the question it is given, right? So be very careful about the units and the way that the problem is given, right? Because in the question it is mentioned that air enters as a flow rate, right? In units 10 meter cube per minute, right? So there you have to consider that. Be very careful, right? So then better say omega 1 equals mv1 dot divided by ma1 dot, right? So then let's write for omega 2. So what is omega 2? So let's write it here. So omega 2 equals what? That is the humidity ratio at the outlet, right? So that equals omega 2 equals mv2 dot divided by ma2 dot, right? But let's consider this omega 2 and omega 1, right? So now we know that ma1 dot equals ma2 dot equals ma dot, right? Now because if you are going to consider this system, right, the flow rate of dry air is the same, right? So then no worries, we can further simplify, right? We can erase ma2 dot and we can write ma dot, and here also we can erase ma1 dot and we can write ma dot, right? So that is how you should simplify it. So now be very careful. Again, there is an intermediate process where we have condensate removal, right? So here we have condensate removal, right? So what do you refer by condensate removal? That means we remove water, right? So for that also there is a particular flow rate of water removal, right? So let's call it mw dot. So that is how you should balance, right? Okay. So now you know. Now we can write the ultimate balanced equation for the water mass, right? So what is it? So that is, here we get the input and this is the output, and in between that we have an intermediate process where we have condensate removal, right? So then we can now write it as m v1 dot, right, mass flow rate of water vapor from the entrance. So that equals mass flow rate of water vapor at the outlet mv2 dot plus the rate of condensate removal mw dot, right. So this is the equation for the balancing of water mass, right. So now we know that the mass flow rate of dry air is the same, right, at here and as well as at here, right. So if you say the dry air mass flow rate at here is ma1 dot, like this, ma1 dot, and the dry air mass flow rate at here, the exit, is ma2 dot, right. So here in this problem that we are going to consider the mass of dry air, right, as a content, it is the same, right. So let's call it ma dot. Got the point, right? Because at the entrance side, right, the air mass flow rate is ma1 dot, right. So this dot represents flow rate, right, and at the exit it is ma2 dot, right. Because here we don't have to consider any flow rate of air mass, right, because here we have condensate removal, right. So then we can call it ma1 dot equals ma2 dot equals ma dot, right. Okay, so this is equation number 1, right. So now we know that if you are going to consider the water content, right, the moisture content, right, so here there is a particular moisture content, right, and here also we have a not moisture, but because it is condensate removal, right, so we have water content, right. So from where it gets that water content, right, so that is definitely from the moisture content over here. Got the point, right? Because the only moisture content that we get into the system is from the entrance side, right. So at the entrance we have the water content or the vapor content as mv1 dot, right. So from there, right, so that equals, that must be same as, right, that water content as a content, it must be the same, right. So that equals mv2 dot plus here the rate of condensate removal, right, mw dot. Got the point, right? So very easy. Now we know that omega equals, right, humidity ratio is what? Vapor content divided by mass of dry air. Got the point, right? So now here we can actually subject this mv, mass of water vapor. So that equals humidity ratio times mass of dry air, right. But be very careful. Here it is the mass of dry air and the mass of the water vapor, but we're not going to consider the equation. Now here you have to consider it as a flow rate, right. So now mv1, right, the mass flow rate of water vapor at the entrance, right. So there you have to consider omega 1, right, that is humidity ratio at the input side or at the entrance side, right. So then what is mv1 dot? So that will be omega 1 times ma1 dot. Got the point? So like that, similarly, right, mv2 dot will be omega 2 times, right, ma2 dot, right, plus the rate of condensate removal mw dot, right. So now we know that ma1 dot and ma2 dot both are same, right, that we have obtained from here, right. So both are same, right. So no problem, right. So now we can replace, right, both these terms ma1 dot and ma2 dot as omega 1 times ma dot, omega 2 times ma dot plus mw dot, right, m small w, right. Got the point? So then now we can subject the mass flow rate of the condensate, right? Right. So what is mw dot? Mw dot will be, that means if I go to subject this mw dot, so it will be what? Very easy, right? ma dot times what? Omega 1 minus omega 2. Got the point, right? So omega 1 you know and omega 2 you know, then what is ma dot? Right? Now ma dot is the mass flow rate of dry air, right? What is ma? What is ma dot? Mass flow rate of dry air. How to find that? Because in this problem we know the volume flow rate of air. We know the volume flow rate, right? And divide volume flow rate by what? Specific volume. Specific volume, right? Because specific volume we know that is 0.889 meter cube per kilogram of dry air, right? As according to the problem, what is the volume flow rate? Volume flow rate is 10 meter cubes per minute. 10 meter cubes per minute. Fine. 10 meter cubes per minute divided by 0.889 meter cubes per kilogram of dry air, right? So now we can find what is the mass flow rate of dry air. That means unit will be kilograms of dry air per minute. So in order to find that, you have to divide 10 by 0.889. So 10 divided by 0.889 will give you 11.25, right? 11.25 kilograms of dry air per minute, right? So now you know what is ma dot. So got the point? So we will write it here. Ma dot equals 11.25 kilograms of dry air in a minute, right? Okay. So then now we can find what is the rate of condensate removal, mw dot. So let's see how to find that. I will erase this, okay? No problem, right? So then mw dot equals ma dot, we know what is ma. Okay, I will write it. Ma dot times omega 1 minus omega 2. Got the point? What is ma dot? 11.25 times what is omega 1 there? 0.0216 minus 0.01, right? So 11.25 multiplied by 0.0216 minus 0.01. So answer will be 0.1305, let's say 0.131 kilograms of water in a minute, right? So that is mw, right? So mw is mw dot, right? The mass, the rate of condensate removal is 0.131 kilograms of water in a minute, right? So now let's see how to find the rate of heat removal, right? Rate of heat removal, right? So in order to find this, right, we need to use an equation, right, based upon balancing the input energy and the output energy, right? Because we have to like balance energy, okay? So then let's construct that equation, right? Total energy, right? Input, total energy input to the system equals, right, rate of heat removal, okay, plus, because now here this rate of heat removal, that is the question that they asked, right, plus, right, energy available at the output, right, because now you know that here there are two outputs, right, one output over here, the another output is the condensate removal, right. So let's write energy available, right, at the outlet 2, right, energy available at the outlet 2, right, because now I have given a label 2 over here, right, okay, plus, right, energy content, right, at the condensate removal, right, because you know that here we have condensate removal at 14 degrees Celsius, right. So then at here also we have a certain energy, right. So then let's write it, right? Energy available at the condensate removal, right, energy available at the condensate removal over here, right. So if you want I can give a label also, so let's give it a label 3, right, so let's give it a label 3, right? Then it is easy for you to understand, right. Let's give a label 3, right, so no problem, right. So now let's carefully apply the values, right. So now this is what they ask, so let's I will give it a notation, right. I will say Q dot, okay, Q dot, total energy input to the system. Now there we know, now we have evaluated what is the flow rate of dry air mass, right, that means ma dot we know, got the point, right. So we know what is ma dot, so that means ma dot times, right, this is dry air mass flow rate, okay, ma dot times h1. What is h1? Enthalpy of dry air, that is given in kilojoules per 1 kilogram of dry air, right. So we know that, and we know the flow rate of dry air, right. So let's call it ma dot times h1, got the point, right. This is Q dot plus, so what is the energy available at the outlet, no problem, right. So what is the mass flow rate of dry air at the position 2, right, so that is also ma dot, because you know that, again I am reminding, right, ma1 dot equals ma2 dot equals ma dot, right, so that is the point. So then we can say, because here also as this equals this, right, so then no issue, right, the dry air mass flow rate at here at the position 2 is also ma dot, right, times, so what is the enthalpy that it is having over there at the position 2, the enthalpy is h2, right, so then it will be h2, but better put brackets. Then energy available at the condensate removal. Now we know the rate of condensate removal, we have calculated that, right. We know the rate of condensate removal that we have evaluated as mw dot, so no problem, plus mw dot we know, multiply that by, so what is the energy content that it is having, that means that is the saturated liquid enthalpy at 14 degrees Celsius, right, what, saturated liquid enthalpy at 14 degrees Celsius, according to this problem it is given as okay, doesn't matter, let's keep it a notation HW, right, what is that, HW, okay, but we know what is HW. HW is actually, that is given in the problem, okay, that is 58.8 kilojoules per kilogram, okay, So now this is the equation. So now Q dot you can find. How to find Q dot? So Q dot equals, so let's subject this one. So we are going to subject this one, right? MA dot times H1 minus MA dot times H2 minus MW dot HW. Got the point? Right. So here you can actually simplify that, right? Shall I erase the top part? Right, I will erase the top part. Right? I hope you have taken this, okay? So now Q dot equals, now you can do the simplification, right? MA dot times H1 minus H2, right? Minus MW dot times MW dot times HW, right? Let's check it. MA dot times H1 minus H2 minus MW condensate removal rate times saturated liquid enthalpy HW. So now what is MA? 11.25. Okay, fine. 11.25. Okay, times what is H1? 85.4. 85.4. Be very careful about the units. Okay, here I am not going to include unit, but be very careful about the units. 85.4 minus what? 39.3. Right, minus MW is 0.131. 0.131. Again, what is the unit? Kilograms per minute. 0.131 multiplied by 58.8. Right. Right. I will erase this part also. Right. So definitely. So then, what must be the unit of this answer? Right. Kilojoules per kilogram, and here we have kilograms per minute. So that means the unit of Q dot must be kilojoules per minute. Okay, be very careful about the units, right? The unit must be kilojoules per minute, right? So now you can take the calculator. Okay, then 11.25 multiplied by 85.4 minus 39.3, right? So that minus 0.131 multiplied by 58.8, 510.9, 510.92 kilojoules per minute. Doesn't matter, you can say 511 kilojoules per minute. So that is the answer.